it's not too misleading. There's a mathematical theorem called the hairy dog theorem.
Hairy dog theorem.
Yes. I mean, that's just a jocular terminology.
Right.
But you think of something which is topologically a sphere. That means, you see, you imagine a dog shape, but you could sort of move it around with a piece of plasticine until it looked like a sphere. It doesn't have holes in it. Okay, forget about its digestive system. You see, you're thinking about the surface outside.
Mm-hmm.
And then the problem is you try to comb the hair on the dog all the way around. And the theorem says there's got to be somewhere where the hair doesn't lie flat. And you try it on a sphere, there's got to be a point where the hair makes a kind of singular point. So it's a bit like that. You have no idea where the singularity is, but you know from general topological reasons that there's got to be one somewhere. And that was the sort of argument that I produced. And I guess a lot of people had a little bit of trouble because they'd never seen this kind of argument. And a lot of people picked up on it, in particular Stephen Hawking. And it became, for a while, many people working on it. I guess it's not so popular now because probably we've run out of theorems.
The idea of a singularity, is when you see something like a quasar or the center of a galaxy,
Mm-hmm.
and we were talking about a black hole. When you say a singularity, what exactly do you mean by that?
Well, the normal expectation is that you have a place, like in the middle of the Oppenheimer-Snyder dust cloud, a point there where the density becomes infinite. And so the curvature of space-time becomes infinite. So you have a place where the equations run away and they go to infinity, and you say, well, something's gone wrong. But maybe initially it was in these very symmetrical cases. But what you could show by these indirect arguments that somewhere something's got to go wrong. You can't continue the equations of Einstein and they get stuck.
Right.
To the place where they go infinite, or what in detail happens, the theorems don't tell you. They just say that something goes wrong, and that's what we call a singularity.
And if a black hole is larger or smaller, the singularity remains constant?
It remains in there. It
remains in there, but it's not measurable in terms of its actual size?
I don't know whether you can measure its size very well, because its size, that's an intriguing question. You might say the size has gone to zero,
right.
But it could be quite complicated and irregular, not like the original Oppenheimer-Snyder one, which is all just even then a point is the wrong point of view, but let's not go into that. No, there is something about the structure of these things you can say. They're not all the same, no.
Then the singularities are not all the same, but the black holes are not all the same.
They're not all the same, but that's one of the strange things about black holes, is that if you let them settle down, they're not all the same to begin with, but there are not many different things they can settle into. They can have rotation, they can have a certain mass, and the mass translates into the size of the diameter of the hole, and you've also got rotation, so they can rotate. And these are, Schwarzschild found the non-rotating ones, and it was Roy Kerr, an Australian, who first produced the solution for a rotating black hole.
Rotating?
Yes, a rotating one. But then you see the remarkable thing is that's what they settle down to. So there are good theorems which tell you that a general black hole, which is very complicated, fairly rapidly will settle down and become one of these Kerr solutions, the rotating black hole.
I remember when I first saw that documentary, and I saw when they were discussing the shape of these galaxies, and that the center of it had this supermassive black hole that was slowly devouring the galaxy.
Yeah.
I mean, it is an unbelievably beautiful yet simultaneously terrifying idea, is that there's this infinite power in the center of infinite mass that's absorbing slowly but surely everything around it.
Yes, but it's not infinite mass. The mass is quite well defined, and it's not infinite. But it's a good question. I mean, if you wait forever, how much of the mass actually gets swallowed by the black hole? You see, I think the picture is to think not just of one galaxy, but a cluster. You see, our galaxy has this 4 million solar mass black hole, and we are on a collision course with the Andromeda galaxy. And I don't know how long, but some time in the future. Yes, the black holes will probably spiral into each other, and there'll be one big one
So it's definable mass, but in infinite density, and that this point, which where they were speculating that this could possibly, in the center of these supermassive black holes, if you could go through that, there would be another universe.
Well,
Is
you
that
see,
just
that's
total
a nice
speculation?
It's a nice romantic thought.
It's more woo. Is it more woo?
I'm afraid so.
Sounds so good, though.
Yes, I know. Well, it's a shame for science fiction because it makes a nice
Well, it's interesting
story.
that we try to make things more complicated than they are because they're so complicated as it is. It's well, like dark matter, for instance. It boggles the mind that we don't really totally understand what 90+%.
Well, that's a good question.
Yeah, what is that stuff?
Well, you want me to tell you my theory here?
Yes, please.
Well, you see, it's part of a story which, I don't know, about 15 years ago, I must have, years are passing by, I can't remember how long ago now. So I had this idea. You see, the universe as a whole is expanding. Now, early in this century, don't ask me dates again, some people, by observing supernova stars, exploding stars, very, very far away, they found out that the universe is actually accelerating in its expansion. And some people found this very mysterious. On the other hand, it's in all the cosmology books because there is that expectation. You see, in 1915, Einstein produced his general theory. In 1917, he introduced what's called the cosmological constant. So you think of it was called lambda. You think of a V shape turned upside down, which is a lambda. And he introduced this term for the wrong reason. Because at that time, there was some indication the universe was expanding, but not very clear. And Einstein, I guess, maybe didn't know or didn't believe it. And the Hubble's observations hadn't yet come to make a convincing case of the expansion. So Einstein thought, well, maybe the universe is static. It's kind of philosophically nice to think that it's sitting there all the time. And he couldn't make it do that. So he had to introduce this term called the cosmological constant. And he did that, and then not very much longer after this, Hubble showed that the universe does seem to be expanding. And Einstein regarded this lambda term as his biggest blunder, which is an irony because it turns out that this term is probably the explanation for the expansion of the universe that we now see. So it's what people call dark energy. I don't like the term very much because it's neither dark nor proper energy in any clear sense, but still, let's not worry about that. Right,
it's an odd term.
Yes, I think so. It's all a little confusing because there's dark matter as well, which is quite different. You mustn't get them confused. But the dark energy, as it's called, or the cosmological constant, which, as far as we can tell, is completely consistent with the observations. It's a positive number, very small, but seems to be producing this expansion. And I'm quite happy with that viewpoint because it leads to a picture which I've been trying to plug for a while now. Maybe up to 15 years, I can't remember. The idea, it's hard to explain, but let me try. It came about because I was worrying about the remote future. And I was thinking, okay, when these black holes are around, they swallowed up all the stars and they're just sitting around. And what's the most next exciting thing happening? Well, the Hawking evaporation. They're going to radiate away. Stephen Hawking showed that black holes had this temperature, extremely cold. I mean, these enormous ones are absurdly cold, much colder than anything made on the Earth. And but when the universe expands and expands and expands, it gets colder than the black holes. And so those black holes become the hottest things around, and so they radiate away very, very slowly, this Hawking radiation. And that carries energy, and so they shrink, and they shrink, and they shrink. And finally, they disappear with a pop. When I say pop, it's probably a pretty big explosion, but not that big from the cosmological, astrophysical scale. So they disappear. Well, it may have been pretty boring when you're sitting around waiting for the black hole to go pop, But afterwards, that's really boring. So this was the picture I thought of, being rather depressed by it, thinking that's our fate. You see, the fate of all the interesting things happening, ultimate fate, is this unbelievably boring final state. Okay, this is an emotional argument, but give me a bit of leeway.
Okay.
So I began to think, well, it's not going to be us who are going to be bored, because we're not going to be around. But the main things that will be around will be photons. And it's pretty hard to bore a photon for two very good reasons. One is it probably doesn't have conscious experiences, now that's sure. So, but the other is more the science point, that they don't measure time, because a photon has no mass. It travels at the speed of light. And the way relativity works, it means that clocks stop, if you like. So if it had experiences, the moment of its creation would be one moment, and the next moment would be infinity. And so they just zip out to infinity without noticing a thing. Now, you see, I'd been doing work on this kind of thing, thinking more about gravitational radiation and how you measure its energy and things like that. And it was a very useful picture to squash down infinity. A useful thing to think about here, if you've seen these pictures by the Dutch artist M.C. Escher.
Yes.
And there are those which are called circle limits. And there's a very famous one with angels and devils interlocking, and they get all crowded up onto the edge. Now, what you've got to think about is that this is a kind of geometry called hyperbolic geometry. And the angels and devils live in that geometry. And the ones right close to the edge think they're the same size and same shape as the ones in the middle. Oh,
there
you got
right
it.
There.
Great.
Yeah.
And so the idea is that if you look at it from the angels and devils' point of view, that's infinity, that boundary.
Mm-hmm.
But from our point of view, we can look at it and we have what's called a conformal map. That picture is a conformal map. What that means is that little shapes are quite consistently drawn, but they can be big or small. And you don't care about whether they're big or they're small, as long as small shapes are accurate, or angles, if you like, are correctly drawn. So it's what's called a conformal map, and that conformal map describes infinity. Now, you can do the same thing to the universe. When I say do it, I mean you can imagine it, where this remote future, you can squash it down, just like in the Escher picture, to a finite boundary. And as far as the things with no mass, they don't have a way of measuring how big or small it is. The Maxwell equations don't know the scale if they don't care. It's work just as well for small as for big, and you can stretch it in some place and squash it somewhere else, as long as the stretching and squashing is isotropic, so just as much one way as the other way, which means more or less that you keep what I call the light cones there. Let's not go into details here, but it means that if you have things without mass, and most particularly the photons, then that boundary is just like anywhere else, and the photons go zipping up to it, and so you might think they've got to have somewhere to go. Okay, well, you don't have to think that, but that was the point of view I had, that the photons need somewhere to enter in a way. But then, where does it go? But then there's the other picture, which is the opposite end. There's the Big Bang. Now you can do a similar sort of trick there, which is stretching it out and making it into a boundary. And that can be done too. I played around with these ideas for a long time, and the standard cosmology models you can do it with. But the more complicated cosmology models, you might have one which is very complicated Big Bang. The general ones don't look like that at all. So you need a condition which tells you that the Big Bang was the very special kind that it was. It's all tied up with this thing called the second law of thermodynamics, and it all ties together with physics in a way which perhaps we don't have time to talk about. But it seemed to me a really good idea to have the condition on the Big Bang that you could continue it in the same way. I should say the idea of doing this was a former student of mine, Paul Todd, who was a colleague of mine, and he used this as conformal continuation as a nice way of saying what the condition is on the Big Bang to give you what you want. But that's a huge condition. But nevertheless, it's what starts our universe off in a very special state, which is what we live off in a way. It's the second law of thermodynamics needs that to get going. Anyway, I don't know if you want to worry about that. But anyway, the point was that it looks as though it's a good condition on the Big Bang that it also should be conformally like a boundary, which if you had no mass, you wouldn't notice it. Okay, you've got particles with mass running around near the Big Bang. But as you get closer and closer and closer, the energy goes up, the temperature goes zooming up. They're zipping around at such a speed that the energy of their motion is much bigger than the E equals mc squared mass, Einstein's mass. The energy in the mass is a certain amount, but when they get so hot, you can forget about the mass. So they, like photons, behave like particles without mass, and so they're just interested in conformal geometry. So the crazy idea I had, not just only you stretch out the Big Bang and you squash down the infinity, but maybe our Big Bang was a squashed down infinity of a previous eon. So I'm saying our eon began with the Big Bang, ended up with this exponential expansion. There was another one before us. There will be another one after us. There was another one before that, and so on.
So it's an infinite cycle of Big Bangs.
That's the picture.
And constant expansion to the point where there's no more energy, and then somehow or another a Big Bang comes out of that again?
Yes, that's right. Well, that's the tricky part that people have trouble with.
It's
Yes.
universally accepted that the Big Bang was an event. There's no
pretty well universally
conflicting theories that are attractive?
I would say nothing terribly popular. There are certain ideas which say you can continue into before the Big Bang. Paul Steinhardt and
what do they think that was?
It has things in common with my model, but it's not quite the same. And you see, it's still. You see, there was not long after Einstein produced his theory, and this Alexander Friedman, who was a Russian mathematical physicist, and he produced the first cosmology models. And one of these was a one which has sort of bounces. A Big Bang, it expands out and then it contracts again. And then it bounces and contracts. And so that was one of his models. The only trouble is if you put irregularities into these models, you get black holes, and these black holes form an incredible mess at the end, and that doesn't join on to a nice smooth Big Bang of the next one. So you have trouble with those models. But still, people take these things seriously. And as I say, Steinhardt and Turok have a model which is like that. So these are things one has to think about. My own view is that they don't take into account the black hole problem, which is that my one gets rid of that because the black holes all evaporate away by Hawking evaporation. And so it forms a model. I used to give talks about this, feeling quite happy nobody would ever prove it wrong, so I can go on talking away at it. But no, I wasn't quite happy with that. I thought maybe you could see signals coming through. So I had one idea about that. But more recently, and this is only just this year, I have two Polish colleagues. That's Krzysztof Meissner and Paweł Nierowski. And there is a Korean who works in New York called Daniel An. And we, the four of us, have a paper which I think today or tomorrow will be the new improved version of this paper, should be on the archive. And the title of the paper is, Are We Seeing Hawking Points in the CMB Sky? Now, what's a Hawking point? You see, I talked about the black holes. See, in the previous eon to ours, assuming it's more or less like ours, there would be black holes in clusters of galaxies, huge, enormous ones, swallowing up pretty well the whole cluster. And what happens to the energy in those black holes? Well, it goes out in Hawking radiation. It takes an age, ages and ages and ages, maybe 10 to 100 years, Google years or something, ages and ages. But all that energy in the picture comes out basically in one point. Think of that Escher picture, and right at the very edge, you see there are an awful lot of angels and devils squashed together there, so that the entire radiation from that single black hole will be squashed into that little point. Now, we're on the other side. What do we see? Well, there will be a big release of energy at that point, and that's what we call the Hawking point, and it spreads out. You see, what we see in the cosmic microwave background, this is radiation coming from all directions, and this radiation doesn't come from the Big Bang exactly. It comes from 380,000 years after the Big Bang. So there's a sort of last scattering surface where photons, which are trying to get out, finally finally can escape, and we see them. Now, that spread out from the Hawking point to what you see in the cosmic microwave background, in the last scattering surface, is something of the diameter of about 8 times the diameter of the moon. No bigger, no smaller. Now, you wouldn't see the whole thing because our past cone, what we see, to cut across it, we don't see the whole thing. But we see probably most of it. So you could imagine something from about 4 to 8 times the moon's diameter, which is a small region which is highly energetic, more energetic in the middle, and it tapers off as you go to the edge. And we seem to see these things. The analysis that the poles, they have the techniques, and the actual analyzing the data, this is the Planck satellite data, was done by Daniel Ann. And then we look at the data and we seem to see an effect, which, see, what you do is we've got only one universe, that's what to complain about, so how do you know if something's real or not? Well, you make zillions of fake universes and you compare this with them. There's a lot of technique about how you do this. But Daniel first did 1,000 of these fakes, and there were sort of 2 sizes of these. You look at these rings to see whether the temperature goes out from the outside to the middle. And there were 2 sizes, both within this size that I say, about 4 degrees across the sky. And there was no evidence of them at all in the simulations. So this is a real effect. Okay, then people were skeptical of this for one reason or another. So Daniel did another, 10,000 altogether. And occasionally there are 1 or 2 which do, 2 or 3 to be precise, where you see this effect in the simulations. But if you work out the probability that this is a real effect, you come up with a confidence level of 99.98% that this is a real effect. So we're waiting to see what people say about this.